Our first task in this assignment is to come up with the derivatives of the four trig functions that involve quotients. So let's write tangent as its definition, sine x over cosine x, and we'll apply our quotient rule for derivatives. So we want low d high, the derivative of sine is cosine, minus the high function, sine of x, times the derivative of the low function, that would be negative sine of x, all divided by low squared. So low d high minus high d low. So here we've got cosine squared, negative times negative, plus sine squared. And I hope you recognize that immediately as our Pythagorean identity. So that numerator is equal to 1. And 1 over the cosine of x then is the definition of secant squared. So we should be able to differentiate cotangent in a similar fashion. By definition, it is cosine over sine. So we do our low function, d high, minus the high function, d low, all over the denominator squared. And now let's be careful about our signs here. Both terms of the numerator are negative. So if I pull that negative, factor a negative out of each part, then we are back to positives in the numerator. And there's our Pythagorean identity again. So our numerator is 1 as long as we keep the negative out in front of the fraction. And there's what we were expecting, negative cosecant squared of x. All right, and then we have secant, 1 over cosine of x. So repeating our quotient rule in each case, low d high, the derivative of 1 is 0, minus high, d low, the derivative of cosine is negative sine, all over the denominator squared. So we've got 0 plus sine of x. So sine of x, and now just to quickly make the point here, I'm going to split up cosine squared so you see how we can write this here. So we've got a sine over cosine, which is our tangent, and we've got a 1 over cosine. So in either order here, we've got secant x, tangent x, if I reverse that process. So the 1 over the cosine here is how I'm coming up with secant. And finishing up our process, cosecant by definition is 1 over sine. So we've got low d high, the derivative of 1 is 0, minus high d low, all over the denominator squared. And we've got a 0 term minus a cosine. And again, if I do the same trick here, splitting up this denominator into sine of x times sine of x, so we see our cosecant and our cotangent. So in either order, there's no special reason why I wrote them in this order. It would be commutative, either order. All right, so now that we know those definitions, we know f prime of x, derivative of tangent, is secant squared. So now we want to find f prime of pi over 3. And to be perfectly honest, I am never in my head doing a secant. I'm always doing a cosine. So I'm thinking of the cosine of pi over 3 is 1/2. The x-coordinate, the short leg of that 30, 60, 90 triangle. So the cosine would be 1/2, so the secant is 2. And we've got to square it. And then we want to do also, if I stick with f, I can do f prime of pi over 4. And maybe I could switch colors here. Pi over 4, remember, I don't know if that looks very isosceles. The legs are congruent, so I prefer, instead of the rationalized form, I prefer 1 over the square root of 2, specifically for this purpose, because I want to do its reciprocal. So the cosine is 1 over the square root of 2, so the secant is the square root of 2. And when we square that, we'll come up with 2. All right, and then we also need to do our derivative of secant, so g prime of x. The derivative of secant is secant tangent. And then let's do at a couple specific points here at our pi over 3 angle. So back to our red triangle. So the secant is the reciprocal of cosine, so that's 2. And the tangent of that angle is the y-coordinate over the x-coordinate, so that's the square root of 3. And then we need to do a g prime of pi over 4. And we've already done the secant. The secant is the reciprocal of the cosine at pi over 4. So the secant is the square root of 2. And the tangent, of course, is y over x. The two legs are congruent. So for a 45-45, the tangent is 1. So those should be our 4 answers for number 2. Question 3, we want to find not just the first derivative, but the second. So the derivative of cosecant, negative cosecant times cotangent. And then we would have to do the second derivative, we'd have to use our product rule. So you could, remember, you can keep a constant out in front of the derivative. So if you want to just handle that negative sign later, or you could consider that negative sign as part of the u glob. That's really up to you. I'll just keep this negative 1 out in front of the derivative. And I'm going to do my product rule. So the u glob times the derivative of v. So the derivative of cotangent is cosecant negative cosecant squared of x. And then I want plus the v glob, oops, let me write that up above, the v glob times the derivative of the u glob, the derivative of cosecant, negative cosecant x cotangent x. And then let's take a look at this. Up to you how you might write this. Perhaps an obvious thing to do here is to factor out a negative cosecant out of each term, since bringing the negative out with this negative 1 already will become a positive. So if I factor a cosecant out of each of those terms, and I factored out the negative, so here I would still have cosecant squared of x, and over here I would have a cotangent squared of x. How much we simplify these is always a matter of time available, and whether you see something that's definitely going to be easier if simplified. When you see 2 trig ratios squared, you might think it's Pythagorean, but if we take our sine squared plus cosine squared equals 1 and divide through by sine squared, notice that we've got a plus minus sign issue here that doesn't make this very easy to simplify. So we could, for example, replace cosecant squared with 1 plus cotangent squared, but I don't think that that's really necessarily simplifying it. So you could write this in several different formats. So notice if I replace it with this binomial, then I would have 1 plus 2 cotangent squared, but that certainly isn't any simpler than the previous. So as long as you clean up the positive negative signs, do as much simplifying as you think is practical. All right, let's press on to number 4. Sketch a graph of e to the x. I think we've now done this several times. So our key point on any exponential function is 0, 1. So we know that at 1 we're up here at e, and at negative 1 we are at 1 over e, and we have a horizontal asymptote of y equals 0 for an exponential function. And we've done this several times now. If you had to sketch the derivative, well, the slope at this point hopefully appears to be 1, and the slopes over here get smaller and smaller, and the slopes over here get larger and larger. So very quickly we realize that the derivative of an exponential function has to look very much like the original function, and for e to the x it is exactly the same. So our y function is the derivative of e to the x is itself e to the x. We've already worked with that. And now let's put that to work in some combination problems. So not very interesting here. If we have the derivative of e to the x is e to the x, what's the second derivative? Well, I think that would still be e to the x. So I could, of course, ask you what is the 87th derivative, and it would still be e to the x. So not too interesting there yet. And here we've got a quotient rule involving e to the x. So we'll take our low function, d high, derivative of tangent, minus the high function times the derivative of the denominator is still e to the x, and then we've got to square e to the x times e to the x is e to the 2x. We might have saved a little trouble there. We're going to factor and cancel here. I hope you can see that you should not leave that e to the x in the numerator, since it can cancel with one of the e to the x's in the denominator. Okay, so I think you can see what's left here. Secant squared minus tangent and now we want to do the derivative here. We got two terms. The first term requires a product rule. The second term, the derivative of the 1, will just be 0, but make sure it doesn't get lost along the way. So we're thinking of this as a product rule. So we've got our u function, leave it alone, times the derivative of the v, secant squared, plus the v term, times the derivative of u, that would be a 6x squared, and then we'd have a plus 0. I just want to make sure you don't forget to go back if there was another term there. Do we need to factor anything out of there? You certainly could factor 2x squared out in front, and you might see it written in that factored form for a multiple choice question, and then we would put this coefficient of 3 in front of the tangent, but just a small change to factor out the GCF. And here I'm always going to recommend that you can leave the square root, but I think most of us find that easier to think of that as the rational exponent. So here we've got a quotient rule. So to do g prime, we want the low function, and that's, you can write it as square root of x if you prefer. Derivative of the high function, negative sine x, minus the high function times the derivative of the denominator, 1/2 x to the negative 1/2, all divided by the denominator squared is x to the first power. Okay, so this was, we didn't have a lot of time on this in the previous assignment, so factoring the GCF here would be some good practice. And the GCF is always, think if you had this term, you guys know that the GCF is the lowest exponent that they share in common. So here we would look at these terms and say, what's the lowest exponent they share in common? The lowest exponent is x to the negative 1/2. So you'll get used to factoring out a negative exponent. And just to make this nice and clean here, we might factor out a 1/2 as well. And then later we can move that 2 to the denominator perhaps. So you might say, well, how can I factor out a 1/2 if there isn't a 1/2 there? Well, to divide, 1 divided by 1/2 would leave a 2. And x to the positive 1/2, here's what I'm doing when I'm factoring, I'm dividing. So I want x to the positive 1/2 divided by 1/2 x to the negative 1/2. So hopefully you'll see that when I subtract the exponents here, that's where I'm coming up with the 2x. And I think I'm going to also, now that I see these both negatives, let's pull that negative out as well. So now we'll have sine x in the first term, and then we'll have a positive in the next term, and I factored out this entire glob, so I would just have a cosine x there. And now we should probably do something about this. So what should we do there? You could move the negative 1/2 down to the denominator, or you could move this exponent, this denominator up here if you want to keep negative exponents. So it's really up to you. I suspect that a more common way of seeing this would be to move them to the denominator. But you know that there are equivalent forms here. So if I move this x to the negative 1/2 down to the denominator, then we're multiplying, so we would add the exponents. So we would have x to the 3/2 power, and if you wish, you could write that as the square root of x cubed, or you could leave it as 3/2. All right, so again, whether you should clean that up or whether you leave it in one of the previous forms, always a matter of decision. Feel free to base that on how much time you have available. If it's not a multiple choice question, then it's up to you how much you simplify. All right, here we've got a product rule. So I have the first function, or the first glob, times the derivative of the second glob, plus the second glob times the derivative of the first. And then let's see what we have here as common terms. Both terms are negative. Both terms have a cosecant. So we might bring that GCF out in front and the negative out in front, so that would leave a sine of x from the first term and a cosine times a cotangent. Is there a better way to write that? You could write it as cosine squared over sine to the first power, but that is not necessarily any simpler to change it into a fraction, so I think we could leave it in this form. And here we've got another product rule. So j prime of x, and I'm going to think of this as x to the 1/3 to do a power rule. So a product, I'm going to keep the first term the way it is, derivative of the second, and let me get some more space here, plus the second glob times the derivative of the first. I bring down the 1/3 and I subtract 1, so I'll have a negative 2/3 power. And here again, let's practice this idea of factor out the most negative exponent. So if I factor out an x to the negative 2/3, and while we're at it, what if we factored out the 1/3? So just to make the remainder look pretty. So now I'm going to take this term and think about factoring it. If I'm dividing this term by 1/3, clearly that's going to leave a 3. You can check if you distribute, will you get back where you came from? That's an excellent way of thinking about this. And if we take x to the 1/3 and we divide it by x to the negative 2/3, we subtract those exponents. So do you see how that works out nicely to leave an x to the first power? So you will quickly get used to this. It happens all the time with derivatives. Factor out the most negative exponent, and it cleans up your remainder. So it brings sort of the problem child out in front, and then the remaining terms are nice and simple. All right, here we have one of those that I could do a quotient rule, but I would not. If the denominator is a monomial, I suspect that we all think it's easier if, and you could write this, think of dividing each term by the monomial. So we're taking each term of the numerator divided by the denominator. So when I'm dividing, I would subtract exponents. So I would have 6 halves minus 1 half would be 2x to the 5 halves. And here we would have x to the 1 half. And then I can do the power rule. So now when I multiply, the 2's cancel. So I have a 5x, and I'm subtracting 1 from the exponent to leave 3 halves. And here when I multiply, I'll get 2x to the negative 1 half. And you could rewrite those with square root symbols, but again, not any simpler. Let's see if we decided to factor out that GCF. Let's see again how it leaves nice clean functions here. So if I take x to the 3 halves divided by, this is what I'm always thinking. I hope you're not going to keep writing this, but factoring is division. So I subtract those exponents and I get x to the, subtracting a negative is adding, so I get x to the 4 halves. So comes x squared. And if you're a doubting Thomas, distribute to see that you'd get back where you came from. And then the second term would just be a minus 2. So factoring out that negative exponent. Factoring out that negative exponent just leaves the nice terms left over. All right, and here we've got, is this n? N prime of x. We're going to do a product rule. So here's our u and v. So our first term, leave it alone, times the derivative of x to the 1 half, plus our second term, x to the 1 half, times the derivative of u is still e to the x. And our derivative of 7, you wouldn't bother. It would be a 0. And now I see that our GCF, I'm going to take out this x to the negative 1 half, and I could take the 1 half out also, so that I don't have any fractions remaining. And e to the x is also a GCF. So here we've taken out the entire first term, so we would just have a 1. And in the second term, we would have an x. And I think that finishes it.